the frequencies in a very unique pattern that's like a fingerprint. And this is really cool because it allows us to identify atoms and molecules in space. If we can find a way to look at these energy that's coming from the molecules in space, we're going to be able to tell what the heck we're looking at. And then a little more about that. So study of light in this way is called spectroscopy. And there are libraries of spectra of all kinds of substances. And this spectra idea is relatively new. It's only a couple hundred years old. And one of the things they did at the Mount Wilson and Palomar observatories, and they were around the turn of the last century, was they had people working there trying to figure out what the characteristic spectrum was of each of these different elements that they might be observing out in space. And the way they did that, for instance, here would be a gas discharge tube containing hydrogen. It's a glass bottle. It's got electrodes on it. And then there's hydrogen inside this. And when you apply a voltage to this, that excites the hydrogen and it gives off this light in these distinct colors. And that distinct pattern belongs to hydrogen and nothing else. And so now all of a sudden, if we see a spectrum with these colors at this spacing, and these spacings relate to their wavelength, and this is in nanometers, so they're really small, you can tell that you're looking at hydrogen. And this is what a spectrum of hydrogen and helium and carbon look like. So how do we get a spectrum? Well, you've all seen one, you just didn't necessarily know it, but when you pick up a CD, it has a whole bunch of little grooves on it, and those grooves act like little triangles, and the little triangles act like little prisms, and the prisms bend the light at very distinct angles. And so as you look, your eye goes across the surface of a ruling, or in this case a CD, you're going to see these different colors because the light has been diffracted at different angles, and your eye and that angle line up so that you see the red, or you see the green, or you see the yellow. And so a real spectrograph looks like this. It's got some sort of source. In this case, astronomers are using a star. The light comes here and gets bent and sent into against this surface, which is like the surface of a CD, and it splits the light into these different colors or different wavelengths. And by tilting this, we can take this pattern and move it across and have it hit this detector. So, oops, didn't mean that to happen. So when it hits this detector, we see the red, and then as we move the mirror a little bit, we see the amount of yellow, the amount of green, and so forth. And by knowing the angle through which we put this grating, we then know what the spacing is between these different colors, and we now have the spectra of whatever we're observing. And this is a diffraction grating for a very high precision telescope that's being used to search for exoplanets. And this is the kind of thing you don't hang on the back of a telescope. You put it in the basement and you send the light down from the telescope to it. But then with this light coming off here, you can see the spectra of what you're observing. And then there's what I've been talking about is emission spectra, where you get something hot, and as it cools, it emits light at a particular wavelength. But also, if you have a sort of source of what you might call white light, which has most of the colors in it, or frequencies, if it hits a gas, some of those frequencies are going to resonate with the incoming light, and the incoming in that will excite the molecules or the electrons in the gas, and it'll absorb that. The gas now is excited by the incoming energy, but that means the incoming energy doesn't come out the far side, and it's been absorbed. So we have absorption spectra, which appear as black lines in a spectra. And so that can let us know what the light that we're receiving, has it traveled through. And so here's an example where we have a white light source here. It's coming towards our telescope. and it goes through this cloud, and this cloud takes away this band of light right here. And this cloud takes away this band of light over here, and this cloud made up of different molecules takes away this light, and you finally get this spectrum, which has these various absorption lines in it. So by looking at absorption lines, you can see what is present in a gas cloud, and you can also, for example, use that to study the surface of the sun or other stars. So both emission and absorption spectra, which are very closely related, essentially the same things in reverse, give us a clue as to what's out there. And this is really just so fundamentally important, because you could look out in space and say, well, what is the sun got? What's it made out of? Is it helium, hydrogen, carbon? What's in the sun? But by using a spectrum, you can actually figure that out. So this is a little bit complicated. I thought I'd take a moment here to see if there were any questions. Can't hear you.
So unmute yourself, Pat, if you want to talk.
Okay. So, but don't the absorption spectra get in the way of whatever is behind them?
Yes, it can.
You have the black lines, because the black lines are generated. Pardon me?
Oh, go ahead.
I was going to say the black lines are telling you that there's some kind of gas or cloud between the telescope and what you're looking at. Mm-hmm. So doesn't that block what you're looking at? So how do you know what's behind it?
That's a good question.
Am I making sense?
No, you are, absolutely. And Frank will give you the answer.
I'll try. You're not actually looking beyond the spectrum. What's happening is the light from the object is coming to you. It's passing through clouds, and when it gets to you, you're looking at the light that appears on your screen smeared out by its spectrum, smeared out into a spectrum by the prism that it passed through. And the presence or absence of lines, if you have bright lines in the spectrum, it's telling you that there's a substance in the original starlight. If you have dark lines in the spectrum, it tells you that there is something in between the light source and you that is absorbing that particular frequency.
Right.
And so the clouds made up of hydrogen will subtract a certain wavelength of light, and so the light that reaches you will be missing that particular wavelength.
Okay.
But what Pat's trying to find out is what's going on in the object behind the cloud, because we don't see its hydrogen line coming through then. Does it have any hydrogen in it? There's got to be an answer, but I don't know what it is.
Well, and
plus the black line doesn't tell you anything, except that there's something there that you can't.
The position of the black line tells you something.
Okay.
Yeah.
Yeah. Now, if there could be a circumstance where there's a bright line, the presence of that object, of that element in the original starlight is a bright line, and it's passing through a cloud that has exactly the same abundance of that same element, which subtracts an equal amount, and you end up not seeing anything. But that would be a very
rare.
That would be a very rare happy circumstance, quite a coincidence for that to happen. Usually what happens is the light from the star has a different chemical composition. The star itself has a different chemical composition than the clouds.
Yeah.
And so you're able to tease out the bright lines from the star and the dark lines from the cloud.
Okay.
It's a very advanced and very mature science.
Well, there's a video coming up that'll help on this subject, Pat.
Okay.
But not this next one, but one not too far after it. So one of the things that we all have heard about, everybody knows about redshift because it's talked about all the time. But here's a little video that explains it, because it's related very much to this idea of spectra. And so I'm going to share this with you. Come on. Oh, come on. Oh, there we go.
Stars are made up of a number of different elements. The Sun is composed of about 73% hydrogen, 25% helium, 0.8% oxygen, and 0.36% carbon, plus smaller amounts of other elements. Each of these elements absorbs certain wavelengths of light. White light is made up of the full spectrum of wavelengths. But the presence of elements such as hydrogen and helium results in black lines in the spectrum. These are the spectral lines for hydrogen, and the black lines appear at the particular wavelengths that are absorbed by hydrogen. Here are the spectral lines for the Sun. By analysing these lines, scientists can tell what elements make up the Sun. And spectral lines can also be used to investigate what elements make up stars and distant galaxies. Scientists can also use spectral lines to work out whether a galaxy, like this, is moving towards the Earth or away from the Earth. Let's compare two sets of spectral lines for this galaxy as we expect them to appear. The positions of the spectral lines are based on the absorption lines for various elements as they have been measured in laboratories on Earth. If the galaxy was moving towards an observer on the Earth, the spectral lines would shift to the blue end of the spectrum. This is known as a blue shift. If the galaxy was moving away from an observer on the Earth, the spectral lines would shift to the red end of the spectrum. This is known as a red shift. The further the spectral lines are shifted, the faster the galaxy is moving away from the observer, and the further away the galaxy is from the Earth. Astronomers such as Edwin Hubble measured the spectral lines of hundreds of galaxies in the visible universe and found that most galaxies display a redshift. This led to the conclusion that the galaxies were moving away from the Earth and that the universe must be expanding.
So, how do we detect these electromagnetic waves that are coming from outer space?
So Peter,
yeah.
can I interrupt just a second?
Yes, please do.
Before we went to the video, Rick had his hand up. He had a question. Do you want to ask your question, Rick?
Well, you essentially answered it. I was thinking that I've always thought that the redshift would shift the spectrums over such that you wouldn't have that overlapping problem if it shifts it over enough. That is, if you're looking at something that's a long ways off, then you'll see the spectrum from the elements that you're looking at shifted over a little bit. And so something between us and that object probably is not moving as fast and wouldn't be as shifted as much. So you would not see those lines blanking out the other things.
I get it. Yeah. I understand what you're saying, and you're right.
Yeah. So, okay.
Yeah.
That was all I had.
Okay. Okay.
Let's see, I had another thought about that. Well, anyway, so this is our another video from the Hubblecast. We've seen several of these, but I like them, and I hope you do. This is our good friend.
Hello and welcome to this fourth special episode of the Hubblecast, celebrating the International Year of Astronomy in 2009. In the last episode, we saw how the advance of technology through the 1970s and 80s revolutionized astronomy. Today, we'll discuss how astronomers detected and measured light over the years, from hand drawings to electronic detectors. 400 years ago, when Galileo Galilei wanted to show others what he saw through his telescope, he had to make drawings. The pockmarked face of the moon, the dance of the Jovian satellites, sunspots, or the stars in Orion. He took his drawings and published them in a small book, The Starry Messenger. That was the only way he could share his discoveries with others. For well over 2 centuries, astronomers also had to be artists. Peering through their eyepieces, they made detailed drawings of what they saw. The stark landscape of the moon, a storm in the atmosphere of Jupiter, the subtle veil of gas in a distant nebulae. And sometimes they overinterpreted what they saw. Dark linear features on the surface of Mars were thought to be canals suggesting civilized life on the surface of the red planet. We now know that the canals were an optical illusion. What astronomers really needed was an objective way to record the light collected by their telescopes, without the information first having to pass through their brains and their drawing pens. Photography came to the rescue. The first daguerreotype of the Moon. It was made in 1840 by Henry Draper. Photography was less than 15 years old, but astronomers had already seized on its revolutionary possibilities. So how did photography work? Well, the sensitive emulsion of a photographic plate contained small grains of silver halide. Expose them to light and they turned dark. So the result was a negative image of the sky, with dark stars on a light background. But the real bonus was that a photographic plate can be exposed for hours on end. When you take in the night sky with your own eyes, once they're dark adapted, you don't see more and more stars just by looking longer. But with a photographic plate, you can do just that. You can collect and add up the light over hours on end. So a longer exposure reveals more and more stars. And more, and more, and then some. In the 1950s, the Schmidt telescope at the Palomar Observatory was used to photograph the entire northern sky. Almost 2,000 photographic plates, each exposed for nearly an hour. A treasure trove of discovery. Photography had turned observational astronomy into a true science. Objective, measurable, and reproducible. But silver was slow. You had to be patient.
The digital revolution changed all that. Silicon replaced silver, pixels replaced grains. Even in consumer cameras, we no longer use photographic film. Instead, images are recorded on a light-sensitive chip, a charge-coupled device, or CCD for short. Professional CCDs are extremely efficient. And to make them even more sensitive, they are cooled down to well below freezing using liquid nitrogen. Almost every photon is registered. As a result, exposure times can be much shorter. What the Palomar Observatory Sky Survey achieved in an hour, a CCD can now do in a few short minutes, using a smaller telescope. The silicon revolution is far from over. Astronomers have built huge CCD cameras with hundreds of millions of pixels. And there's more to come.
The big advantage of digital images is that they're, well, digital. They're all set and ready to be worked on with computers. Astronomers use specialized software to process their observations of the sky. Stretching, or contrast enhancing, reveals the faintest features of nebulae or galaxies. Color coding enhances and brings out the structures that would otherwise be difficult to see. Moreover, by combining multiple images of the same object that were taken through different color filters, one can produce spectacular composites that blur the boundary between science and art. You too can benefit from digital astronomy. It has never been so easy to dig up and enjoy the amazing images of the cosmos. Pictures of the universe are always just a mouse click away.
Robotic telescopes equipped with sensitive electronic detectors are keeping watch over the sky right now. The Sloan telescope in New Mexico has photographed and catalogued over 100 million celestial objects, measured distances to 1 million galaxies, and discovered 100,000 new quasars. But one survey is not enough. The universe is an ever-changing place. Icy comets come and go, leaving scattered debris in their wake. Asteroids zip by. Distant planets orbit their mother stars, temporarily blocking part of the star's light. Supernovas explode, while elsewhere new stars are born. Pulsars flash, gamma-ray bursts detonate. Black holes accrete. To keep track of these grand plays of nature, astronomers want to carry out all-sky surveys every year, or every month, or twice a week. At least that's the ambitious goal of the Large Synoptic Survey Telescope. If completed in 2015, its 3 gigapixel camera will open up a webcam window on the universe. More than fulfilling astronomers' dreams, this reflecting telescope will photograph almost the entire sky every 3 nights.
Thank you for joining me in this 4th episode of the special series. Next time we'll see how telescopes can study the universe that we can't see with our own eyes. This is Dr. J, signing off for the Hubblecast. Once again, nature's surprised us beyond our wildest imagination.
So he mentioned the Large Synoptic Survey Telescope, and it was supposed to be online in 2015, but it's way behind schedule, and now I see on the web that they're thinking 2023. This is sort of a cross-section looking through it, and it recently got named the Vera Rubin Large Synoptic Survey Telescope. And Vera Rubin worked for the Carnegie Institution in Washington in their terrestrial magnetism department, but she was actually an astronomer. And they have an astronomy group out in California that's part of the Mount Wilson, what was part of the Mount Wilson Observatory. But she was smart enough to stay away from all those men and work on her own, and made some very significant achievements, and got this telescope named after her. And Frank mentioned her in this talk that he gave on about women in astronomy, just that he gave very recently. But what's happened is because of the CCDs have come down in cost, and we can buy these home cameras and stuff, you can have an amateur in their backyard with a 10-inch telescope take an image like this. This is a picture taken by Stephen Rule, who's a member of BPAA, and it was done right here in his backyard in Bainbridge Island. So it's astounding what an amateur astronomy can do. And Pat, there you go. So is there any discussion about detectors? It's changed dramatically.
I have a question about that picture. What is the picture that he took of?
It's a picture of a supernova explosion, the remnants from it, but I don't know where it is or when it took place. If you look really carefully, way down in the middle, there's a remnant right there in the middle, which is probably the effect of a neutron star that I would guess that's in there. I don't know much about this particular object, but when a star of a certain size goes through its life cycle, it will explode, and then the remnants will spin up and become a dense object of neutrons, and it's rotating very fast. These neutron stars can rotate at many revolutions per second, and so it's like a ice skater who pulls in their arms when they're doing a pirouette and they speed up. Well, the same thing happens with a neutron star. As it collapses, the angular momentum stays the same, and so if a smaller radius, you have to go faster in order to conserve the momentum. So these things really, really whip around. And this looks like at some time in its life had some very prominent jets coming off of it, but I don't know whether they came off before it blew up or that's part of it. I just don't know enough about this object. But it does blur the distinction between science and art. I mean, that's just a gorgeous picture. More questions?
Will the colors in his image be different than someone else's photograph?
They may be, because one of the things you can do with this digital stuff is you can take a slider on his computer screen in his living room while he's managing his telescope outside in his yard, is to slide a green slider for more green, less green, more red, more blue, and you can actually tweak that. So there's this question of, well, what's real? And in a way, it doesn't too much matter, because what you're trying to do is tease out the things. If you're doing it as an art object, you tease out to look really cool, but are really interesting. But if you're doing it for science, you may say, well, the blue stuff is all associated with high energy ultraviolet things, and that's the thing I'm really interested in this studying about this object. So you look at those more intensely than you do the red stuff. So, and you can do this after the fact or during the time when you're actually taking the exposure. But that's again back to what Dr. I've forgotten his, I should know his name by now, was talking about how because they're digital, you've got the opportunity to tease out of the image many things that if it's, when I was growing up, this would all be on a black and white plate. You wouldn't have any color at all. And so then, you know, it's much harder to see what's going on. But now with the digital CCDs and color enhancement and color filters, you can learn a lot more.
So you can tell from looking at this photo that if you look at the stars, they're not white. They've got kind of a bluish cast to them. At least on my monitor, they do.
Yeah.
If you see that on your monitor, then and that's a hint that the whole image has been shifted slightly to the blue, and you can kind of keep that in the back of your mind when you're looking at this picture. But I think the red is pretty accurate.
Yeah. Yeah. Anything else about detectors? And as far as these CCDs work with spectra as well as with direct imaging, so that the important work that's done with spectrum to find out what the composition of objects are relies on these same types of detectors. So let's go on with another one of these Hubblecast videos. This one's called Seeing the Invisible, and it's
aka Dr. Joe Liske.
When you listen to your favorite piece of music, your ears pick up on a very wide range of frequencies, from the deepest rumblings of the bass to the very highest pitched vibrations. Now imagine your ears were only sensitive to a very limited range of frequencies. You'd miss out on most of the good stuff. But that's essentially the situations that astronomers are in. Our eyes are only sensitive to a very narrow range of light frequencies, visible light, but we are completely blind to all other forms of electromagnetic radiation.
Oh, I'm sorry, excuse me. Sorry.
Aka Dr. Joe Liske.
When you listen to your favorite light, but we are completely blind to all other forms of electromagnetic radiation. However, there are many objects in the universe that do emit radiation at other parts of the electromagnetic spectrum. For example, in the 1930s, it was discovered by accident that there are radio waves coming from the depths of space. Some of these waves have the same frequency as your favorite radio station, but they are much weaker, and of course there's nothing to listen to. In order to tune in to the radio universe, you need some sort of receiver, a radio telescope. Now, for all but the longest wavelengths, a radio telescope is just a dish, much like the main mirror of an optical telescope. But because radio waves are so much longer than visible light waves, the surface of a dish doesn't have to be nearly as smooth as the surface of a mirror. And that's the reason why it's so much easier to build a large radio telescope than it is to build a large optical telescope. Also, at radio wavelengths, it is much easier to do interferometry. That is, to increase the level of detail that can be seen by combining the light from two separate telescopes as if they were part of a single giant dish. The Very Large Array in New Mexico, for example, consists of 27 separate antennas, each measuring 25 meters across. Now, each antenna can be moved around individually, and in its most extended configuration, the virtual dish mimicked by the array measures 36 kilometers across. So what does the universe look like in the radio? Well, for a start, our sun shines very brightly at radio wavelengths. So does the center of our Milky Way galaxy. But there's more. Pulsars are very dense stellar corpses that emit radio waves only into a very narrow beam. In addition, they rotate at speeds of up to several hundred revolutions per second. So in effect, a pulsar looks like a rotating radio lighthouse. And what we see from them is a very regular and fast sequence of very short radio pulses, hence the name. The radio source known as Cassiopeia A is in fact the remnant of a supernova that exploded in the 17th century. Centaurus A, Cygnus A, and Virgo A are all giant galaxies that pour out huge amounts of radio waves. Each galaxy is powered by a massive black hole at its center. Some of these radio galaxies and quasars are so powerful that their signals can still be detected from a distance of 10 billion light years. And then there's the faint, relatively short wavelength radio hiss that fills the entire universe. This is known as the cosmic microwave background, and it is the echo of the Big Bang, the very afterglow of the hot beginnings of the universe.
Each and every part of the spectrum has its own story to tell. At millimeter and sub-millimeter wavelengths, astronomers study the formation of galaxies in the early universe and the origin of stars and planets in our own Milky Way. But most of this radiation is blocked by water vapor in our atmosphere. To observe it, you need to go high and dry. To Llano de Chatanator, for example. At 5 kilometers above sea level, this surrealistic plateau in northern Chile is the construction site of ALMA, the Atacama Large Millimeter Array. When completed in 2014, ALMA will be the largest astronomical observatory ever built. 64 antennas, each weighing 100 tons, will work in unison. Giant trucks will spread them out over an area as large as London to increase the detail of the image or bring them close together to provide a wider view. Each move will be made with millimeter precision.
Many objects in the universe also glow in the infrared. Discovered by William Herschel, infrared radiation is often also called heat radiation because it is emitted by all relatively warm objects, including humans. You may be more familiar with infrared radiation than you think, because on Earth, this kind of radiation is used by night vision goggles and cameras. But to detect the faint infrared glow from distant objects, astronomers need very sensitive detectors, cooled down to just a few degrees above absolute zero in order to suppress their own heat radiation. Today, most big optical telescopes are also equipped with infrared cameras. They allow you to see right through a cosmic dust cloud, revealing the newborn stars inside, something that just cannot be seen in the optical. For example, take this optical image of the famous stellar nursery in Orion. But look how different it is when seen through the eyes of an infrared camera. Being able to see in the infrared is also very helpful when studying the most distant galaxies. The newborn stars in a young galaxy shine very brightly in the ultraviolet. But then this ultraviolet light has to travel for billions of years across the expanding universe. The expansion stretches the light waves, so that when they are received by us, they've been shifted all the way into the near infrared.
This stylish instrument is the MAGIC telescope on La Palma. It searches the sky for cosmic gamma rays, the most energetic form of radiation in nature. Lucky for us, the lethal gamma rays are blocked by the Earth's atmosphere, but they do leave behind footprints for astronomers to study. After hitting the atmosphere, they produce cascades of energetic particles. These, in turn, cause a faint glow that MAGIC can see. And here's the Pierre Auger Observatory in Argentina. It doesn't even look like a telescope. Pierre Auger consists of 1,600 detectors, spread over 3,000 square kilometers. They catch the particle fallout of cosmic rays from distant supernovas and black holes. And what about neutrino detectors? Built in deep mines or beneath the surface of the ocean, or in the Antarctic ice. Could you call those telescopes? Well, why not? After all, they do observe the universe, even if they don't capture data from the electromagnetic spectrum. Neutrinos are elusive particles that are produced in the sun and supernova explosions. They were even produced in the Big Bang itself. Unlike other elementary particles, neutrinos can pass through regular matter, travel near the speed of light, and have no electric charge. Although these particles may be difficult to study, they are plentiful. Each second, more than 50 trillion electron neutrinos from the sun pass through you. Finally, astronomers and physicists have joined forces to build gravitational wave detectors. These telescopes do not observe radiation or catch particles. Instead, they measure tiny ripples in the very structure of space-time. a concept predicted by Albert Einstein's theory of relativity. With a stunning variety of instruments, astronomers have opened up the full spectrum of electromagnetic radiation and have even ventured beyond. But some observations simply can't be done from the ground. The answer? Space telescopes.
So he mentioned the Atacama Large Millimeter Array Telescope and said that it was just under construction, but it's since been finished up. And here's a gorgeous picture of some of the telescopes themselves at the site in Alma, or site in Chile, and it's at 16,000 feet. So it's very high up in the sky, and you don't get much, there's not much atmosphere. You're well above half of the atmosphere. The atmosphere, you're halfway through the atmosphere in terms of the number of molecules when you get to 12,000 feet. So this is well above that, and the atmosphere is really quite thin. But this looks in what's called the millimeter wave length, and here is an example of an object observed in millimeter waves. And you'll notice that, again, if we looked at that, well, we can't see that. We just don't know what color it is. But so we have to arbitrarily assign colors. We also assign in more intense colors or a more intense of a given color, like right here. This is something that has more energy than the space out in here. It's more intense. So you can have a brighter and dimmer of a given color, and then you can also change the colors depending upon what it is that you're detecting. And that is related to the frequency or the wavelength that your telescope is looking in. So I don't know these frequencies, but at some frequency, F1, you get this, you're sensitive to this red light. Over here, you're sensitive to something blue, and you can distinguish those and then assign a color to them. And so it gives you a way to visualize or see the invisible, which is really quite nice. There's another effect that we haven't talked about, magnetism. Light is actually an electromagnetic wave, and there's all kinds of magnetic activity, particularly in the sun, but also all over in space. And it's hard to detect magnetism from a distance. And I'm not going to go into this in any depth, but this, first of all, let me introduce this. This is the McMath Pierce Solar Telescope Facility outside of Tucson, Arizona. And there's a big heliostat up here, which takes the light from the sun and reflects it down this tube to a concave mirror, goes back up here and goes down into here into a stellar spectrograph. So this is where they can make one of those spectrums that we were talking about earlier and look at all the different colors and find out, as we saw, that there's a certain percentage of oxygen, certain percentage of carbon and so forth in the sun. And we can see the effect of magnetic fields when we look at sunspots, but it's kind of hard to measure the intensity of that. And somebody by the name of Zeeman figured out that if you take light and you pass it through a magnetic field, that the light will split into two frequencies that are very close together. They're only separated by a few megahertz, and they counter-rotate in polarization. And so all of a sudden, Mother Nature's given us another way to measure something at a distance that would be very difficult to do without making use of this Zeeman effect. And the magnetism in the sun is affecting the light and creating this split in frequency, and that can be observed in these spectrographs. And I can't give you too much detail on that, but my point is that it is possible to measure magnetism in space. So let's go on a little bit here. We talked earlier about the James Webb Telescope, and this is going to cover the infrared, near infrared and far infrared wavelengths, and that's going to be launched, who knows, 2021. But then we've also set up the Chandra X-ray telescope, sent up the Fermi Gamma Ray telescope, an extreme ultraviolet explorer, and the Astro Japan X-ray telescope. And I did a little calculation here if I can find my piece of paper. Oh, yeah, there's been 10 X-ray telescopes, gamma ray telescopes put up, 33 X-rays, 19 ultraviolet, 9 visible telescopes, 8 infrared and some millimeter wave telescopes, and a couple of microwave telescopes. So we've really tried to cover the spectrum, with the various kinds of telescopes that have been put up. And part of the reason for that is, as you said, the high frequency stuff like X-rays and ultraviolet won't make it through our atmosphere. So the only way to really get good measurements is to get up above the atmosphere. So we've spent a lot of effort over the last 40 years putting up various kinds of telescopes. So I'm going to shift gears a little bit, and this might be a time if somebody wants to ask questions about spectra or wavelengths or redshifts or whatever. And I'm going to, this next topic.
What about neutrinos?
Oh, yeah. When the nuclear reactions take place in a place like the sun, the physicists can calculate all the different energies that have to be accounted for during those reactions. And when they do the arithmetic, they kept finding out that there was something missing. And there was one piece of energy that we couldn't detect, but by the equations, we knew it had to be there. And that got the name neutrino because it was known that based on the physics that it would be a neutral particle, and it would probably be teeny, and so it became the neutrino. And so there was a hunt for the neutrino, and it is a particle that doesn't interact with regular matter hardly at all. It's that they said trillions of those go through your body every second. We're just flooded with neutrinos. And so finding them and making these equations balance was a big search. And the way they did that was to build some great big underground cavities, filled them up with various chemicals. I forgot, they use, Frank, do you remember what they put in some of those?
Essentially, it was cleaning fluid
Yeah.
of some sort, but it was a common chemical. Yeah.
Yeah. They were looking for something called Cherenkov radiation, where the neutrino, when it bangs in, very rarely, but when it hits something, then it gives off a secondary form of radiation, which detectors in this large chamber can detect. And there was a big monumental event when we finally started to detect them. But then a new problem showed up. We didn't detect enough of what we expected. And so they found out later on that there are 3 types of neutrinos, and that they can change their flavor or their type as they transit through space. And so they've changed the methods of detectors and have observed all 3 types now. And that makes the equations balance. They had to be there, but we couldn't see them. It just wasn't working. So that's how they got figured out. But
fascinating. Yeah, amazing.
Yeah, and and again, the darn things go through us. We have no idea that we're being flooded by them. They'll go right through the earth, and they don't even slow down. They just keep going. But every once in a while, they will react, and it is possible. We've been clever enough to make detectors.
So I'm looking on Wikipedia right now, and there are several types of detectors, but it seems like water is the most common medium that's used. Another type of detector is using a mineral oil as the detector, and another one is using ultra pure heavy water as opposed to normal water. There are some detectors 2.5 miles deep in the Mediterranean Sea, no, 2.5 kilometers deep in the Mediterranean Sea, using the seawater itself as the detector.
One of the first things they did was they put a detector and they put it near a nuclear reactor, because they knew that a nuclear reactor would also be emitting these kind of particles. And sure enough, it showed up there, and then they began to detect the ones coming from the sun. Okay.
Yeah.
All right, let's go on to exoplanets. You know, we've always wondered whether we're alone in the universe. You recall in the first class, not only were we alone, but we were it, and we were in the center of it, and everything rotated around us, and we were just like children. We know that we're the most important thing in the whole world. Well, maybe we are, but it's that we've since gotten ways where we can begin to detect whether there are other planets. And nobody knew, and there was a strong suspicion that there would be, but until they're detected, you really don't know. So exoplanets, what by that means is that we're looking for what amount to other solar systems, and they're going to be far away from us. And their planets, as we are small compared to their host star, and they're going to be dim compared to their host star. We can only see them by the reflected light. And so it's a really hard thing to look for. And that search only got in earnest probably in the 70s, I think. And there are two methods for it. One is called the Doppler shift. And this is something you might not intuitively think, but when two bodies are in orbit around each other, they orbit about a point that's the center of mass of the two objects. So when the moon rotates around us, the center of mass is between the mass of the moon and the mass of the Earth is actually in a point below the surface of the Earth, but nevertheless, it's not in the center of the Earth. And so the Earth actually moves a little bit towards the sun and a little bit towards away from the sun every time the moon goes around us, because it pulls it away or pulls it towards. And because the gravity is operating in both ways. And so you can see that motion when a planet goes around a star, and the speed of that motion can be measured using redshift. Remember, we've now figured out with spectra how we can measure how fast something is moving towards us or away, and so that we can look at the spectrum of stars and observe that the star might be coming towards us and then going away and so forth. So here's a kind of a cute little video showing this effect of the Doppler shift.
We now know that there are planets orbiting other stars besides our own, but it's generally very difficult to see these planets directly, given their stars are 1 billion times brighter than them. So to discover them, we have to try measure their effect on their star. In this video, we're going to see different ways to use the effect of gravity. The idea is simple. We're used to thinking of planets being pulled around by the gravity of their star, but remember, gravity acts both ways. The star also gets pulled by the planet. So even though we're used to thinking that the planet orbits the star, that's only approximately true. Actually, what happens is both the star and the planet orbit the center of mass of the system. So if we see the star wobbling around like this, we can conclude that there is a planet there. But we can actually learn a lot more about this planet if we watch its stars wobble carefully. Remember that both the planet and the star orbit the center of mass, so if the planet is here, the star must be on the other side, or else this isn't the center. Then you see the star takes exactly the same amount of time to do a full orbit as the planet does. So, if you can measure the star's period, it tells you the planets. But then you can use Kepler's laws to find out how far away the planet is from the center. There's one other piece of information that the star's movement reveals about the planet. Suppose this planet is very heavy, then the center of mass will be a bit closer to it, which means the radius of the star's orbit is bigger. Another way to think of this is, the radius is bigger, but it still takes the same amount of time to complete an orbit, so the star must be going faster. So if we can either directly measure the radius, or if we could measure the speed of the star, then we'd know about the mass of the planet. So basically, the two things we're interested in measuring about the star are the period of time it takes to complete an orbit, and either the radius of that orbit or the speed of the star as it goes around. There are two ways to get this information. The most obvious way is to precisely measure where the star is over time, which lets you observe the period and radius of the wobble directly. This is called astrometry. But think about how difficult that can be. The star doesn't generally move very much, and if that's compounded by the star being far away, it can be very hard to directly see the star moving at all. That's why the second method, called the Doppler method, isn't about measuring the star's position, but its velocity. Think about it like this. When the star is over here, it's moving towards us, but that means the light coming from it is a bit blue shifted. On the other hand, when it's on this side, it's moving away from us now, so it's red shifted. So if we keep measuring how shifted the light is, we can figure out when the star has done a full orbit. So, just like the astrometry method, that gives us the period of the planet. Now, to figure out the mass, remember the faster the star is moving, the heavier the planet must be. But if the star is going fast, then this blue and red shift is bigger, so we can work out its speed from that. Then, in theory, we can get the same information from the Doppler shift data as the astrometry data. But in practice, Doppler shifts can be measured to way more accuracy. In fact, with this method, we would be able to detect if the star was going at walking speed. But there is a limitation with the Doppler method. Imagine if, instead of being side-on, the star moved like this. Now the star is never moving away from us or towards us, so its light is not blue or red shifted, and so we can't tell that it's moving at all. Measuring Doppler shifts only tells us the component of the velocity in our direction. That can lead us to underestimate the mass of the planet, or in the worst case, we won't be able to tell that there is a planet there at all. So that's how the astrometry and Doppler methods work, and their pros and cons. I said that both methods let you estimate the planet's radius and mass, but I only gave you an outline of how to do that. If you're interested in testing yourself, figure out how you do it from the raw data.
Okay, isn't that cool? And that was first done at Lick Observatory in California, and it's since been done a lot in all kinds of different places. The other way you can do it is with what's called transit dimming. If the line of sight between the star and us also includes the plane of the planet, when the planet goes in front of the star, it'll block some of that light. So if we have a very well calibrated light detector, and then we see the light dim, and then we see the light come back up, we can get an idea of the size of the planet, and then we can also measure the period. So, and then the time, so the time of the repeated thing will give you the period. And this measurement is made just with a photoelectric. It doesn't involve a spectrum. It's just done with pure brightness. So here's a schematic to show you kind of how transit works. You have the planet going around in its orbit. It crosses in front of the star, and you get this dimming taking place. The shape of this curve is important because it'll tell you the relative size of this planet, and then the light gets to a minimum, and then as the planet leaves the edge, it raises back up. And so this light curve gives you the same kind of information that you would get from the gravitational, the Doppler effect. And this is a hard measurement to make, particularly from the ground. And so we put up the Kepler telescope as an exoplanet hunter. It's now out of service, but it recorded how many thousand, if I wrote it down? Oh yeah, 530,000 detections of stars that had dimming associated with them from planets crossing in front of them. And 2,662 of those were, they made the measurements on 530,000, and 2,662 of them actually had planets moving in front of them. And so it's been real serious detection of planetary systems. And we still don't have any way to see them, although there is hope with some of the new telescopes that'll come along that we might be able to resolve an actual planet in orbit around another star.
So Peter, that's actually been done now. There has been a photograph taken of, actually, we have gotten a photograph of the planets themselves with a telescope equipped with a corona mask that blocks the starlight.
Right.
And it just recently happened. I'll try to find a link to that and put it up. But yeah, we've actually seen it now.
Oh, that's cool. So this is a little bit old data. This is as of 2016. And it's interesting that 4-year-old data is now considered old data. That shows you how fast things are changing. But, and this is a hard one for you to read, but these are Mercury-sized planets that they think they've observed. These are Earth-size. These are Neptune-sized planets. These are a little bit bigger than Neptune. Have I got that? Am I reading that right? Even I can't read it. Oh, these are super Earth size right here. Sub-Neptune size, Neptune size, Jupiter size, sub-Jupiter size, Jupiter size, and bigger than Jupiter. Sorry. So what you can see though is what we're detecting seems to fall in some sort of region here where things a little bit smaller than Neptune have been the ones that we've been able to detect. That doesn't mean there aren't more at both ends of this spectrum that we have here, but that's what the data shows so far.
And I might add, there's a telescope a space telescope up there right now called Gaia, that is an ultra-precise astrometric telescope that is measuring those very precise positional changes of stars. And it's detecting, not only detecting exoplanets, but it's also determining that there are many stars that are all moving in the same direction and that have the same, roughly the same chemical composition. And this is telling us that these are streams of stars that are the result of small galaxies that have collided with and been absorbed by the Milky Way. That's how precise the measurements have gotten with this Gaia telescope.
That's really cool. I haven't planned to talk much about this, but you can imagine that some of these, one of the obvious things, if these planets that we do detect are going to have life on them, they've got to be in a certain zone. They've got to be where there can be, we think, where there has to be liquid water. There has to be some form of atmosphere. They can't be too hot, they can't be too cold. And so that zone of habitability is called the Goldilocks zone. And the ideal thing would be to discover some Goldilocks zones and then check their atmosphere and see if they've got CO2 or what they have in their atmosphere and get some idea whether there might possibly be life of the, at least of the kind that we know. And so stay tuned, and that hunt will be continuing. So I want to begin to wrap up here actually, but here is kind of my favorite picture. This is Centaurus A, which is a galaxy, and it's an image taken with many different wavelengths, each of the different wavelengths superimposed on the other. And you can see a lobe of jets coming out of a central hole that's in the middle, which has about 55 million solar mass black hole. Oh, can you hear the sirens?
Yeah.
Sorry, let me wait a second till they go by.
They're not too loud, Peter.
All right. Okay. So 3 different instruments at very different wavelengths produce this picture. There's 870 micron sub-millimeter data, which is in orange. So this is radio wave emissions coming from this. The blue things are from the Chandra X-ray observatory, and that's X-rays, and that's long wavelength radio waves. So you can see that This is in a very wide range, and this is why we want to be able to look way beyond just the visible to see what's going on. And then, of course, there is the visible light in that. So, and this was taken from a telescope in La Silla, Chile. But somebody took the trouble to combine these images and make this what you could see. If your eye could see from X-rays down to radio waves, that's what that object would look like. And then here's a little bit more about it. This is not as pretty, but this is more, has a lot of information in it. Here's the same galaxy. And then superimposed on are these various clouds of hydrogen and these green clouds. And then there's radio knots, they call them here. There's X-ray knots. So these are places where there's a lot of X-ray energy coming out. And this is radio things. So things are happening here as electrons are being accelerated and spiral around as they've been shoved out of the center of this galaxy by activity probably around the black hole. But again, this just shows you the utility of being able to look in all these different wavelengths so that we really can see the invisible. Oh, that's interesting how that worked. So what we've talked about is the frequency limitation of the eye, electromagnetic radiation, wavelengths and frequencies, the spectrum, and the fact that spectra are unique fingerprints. It lets us see whether there's oxygen or hydrogen or carbon or ammonia or any number of other things out in space. And we talked a little bit about emission and absorption spectra. And then we talked about spectrographs, which are the instruments that are used to make those measurements. And then we talked about redshift. And then this had already come up, so I didn't quite do my homework. But there was the video on detectors. There was the one on seeing the invisible. I talked briefly about using the Zeeman effect to visualize magnetism. And then we talked about the high frequency telescopes. The telescopes for high frequency research, exoplanets, and then my favorite multi-wavelength image. So, geez, we're a little bit early tonight, unless there's more questions. But this is what we covered tonight in session 3. And next week, we're going to go and talk about the Big Bang and the expansion of the universe and gravity waves. So if there are any questions or comments. Yes.
I have a question. Has spectroscopy, is that right?
Yes.
Has that led to any discovery of new substances or elements from space that we don't have on Earth?
No, not to my knowledge. I think, no. We've actually found many things on Earth that you don't find in space because we've, through nuclear reactions here in accelerators and in nuclear energy plants and stuff, we've been able to produce unstable elements which are high in atomic number and their centers are wobble around and they spontaneously come apart. And so they're not stable but we can create them in the laboratory and then they go away. So those may be out there, but they don't last very long. I'm sure they exist. Well, I'm not sure, but I suspect they exist when the very high energy explosions like occur in a supernova, but they decay away very quickly and become other elements. They'll decay to lead or plutonium or something like that. Well, in fact, plutonium is one that we created here. I don't think you'll find it out in space. So no, but we can not only detect elements, but we can detect molecules. So we can see ammonia, we can see water, we can see all other common chemicals that you wouldn't necessarily think would be out in space. I mean, what caused ammonia to form out beyond the Oort cloud? Well, I don't know. I can't tell you, but maybe somebody can.
So, Peter, there's actually an interesting story about helium. Helium gets its name when the periodic table was first put together. Helium had not been discovered, but we knew that there was an element that belonged in that spot. that would have those characteristics, but it was not ever found on Earth, and it wasn't until an astronomer, a woman astronomer in fact, detected the spectrum of helium in the light coming from the sun, and because the sun in ancient times was known as Helios, the element was given the name helium, and so it was first discovered on the sun. Once we knew it existed, then it was eventually found on Earth. But yeah, that's how helium got its name.
Well, that's good to know. I didn't know that.
Yeah.
And we're running out of helium, right?
Yeah. Yes, we are.
Well, if you stay tuned for another 4.5 billion years, then all the hydrogen in our star sun will have been used up, and then we'll turn into a red giant, and then we'll fade away as a white dwarf. But we won't be around to have that happen. Something else much worse might have happened in the meantime. But anything of that kind will make COVID look trivial.
So maybe I don't know if I misunderstood this, but how much does the sun, and thus what orbits the sun, move in space?
Well, a couple ways to answer that question. The solar system itself, including the sun, is moving around our galaxy as a group. And then the sun has the planets moving around it, and there's a center of mass of that system. But if you think about it, depending upon how the planets are aligned, the center of mass of that system shifts a little bit. And so the motion, the so-called proper motion of the sun, is a very complex shape that relates to the number of planets and where their position is. And let's see, what was I?
Are we in the, do we just keep more or less going around the same space, or where we're rotating right now is nowhere near where it was a year ago?
Oh,
that makes sense. Or 100 years ago, or 1,000,000 years ago.
Frank, do you remember the solar system's velocity? I think we're 22 miles a second around the sun, but I think the solar system itself is moving faster than that.
Yeah, the sun and all the planets going with it. The sun is moving around the center of the galaxy, independently of any other stars. Some stars maybe are moving generally in our direction, others are moving in other directions, but we're generally moving around the center of the galaxy, and I could quickly Google that and find out with what velocity, but it's pretty fast. I think it's something like, oh, I don't know. But I'll find that out. But to answer your question is yes, the solar system as a whole is trailing along with the sun as we orbit the center of the galaxy.
And Vin, you've touched on something. The video that with a cartoonish sort of video of the Doppler effect on and the movement around the center of mass, that only implied one planet. But if you've got multiple planets, the apparent motion of that star gets a lot more complicated because it moves towards you depending upon what I'm going to use the fancy word, the vector, the gravitational vectors of the different planets that are in orbit around, how those sum up mean that where the star goes is a little bit different than a straightforward thing. But you can make the measurements over a period of time, and then you can do what's called Fourier analysis, and you can find out the frequency components of that motion and then determine what the planets are. But that's it's being done. It has to be done because you almost never find a star with just a single planet on it. It usually has multiple.
So the answer is 828,000 kilometers per hour is the speed of the sun around the center of the Milky Way. And if I take that and divide it by 1.6, I get 517,500 miles per hour. And then what? You divide that by 60, and then divide by 60 again, and it gives you about 144 miles per second. The sun is moving around the galaxy. So there.
And then I think my recollection is that we're moving as a planet at about 21 miles per second around the sun itself. But you don't notice that.
No, you don't notice it at all.
Oh, let me stop the screen share here.
Any other questions? Everybody knows everything. That's great.
Well, I apologize. I got to ask a couple stumper questions tonight.
Well, Janie's waving her hand. Do you have a question, Janie?
Yeah. How long does it take the sun to orbit around the center of the Milky Way?
Okay, I still have this page open, and there's the answer.
I think it's 240 million years.
230, yeah, 230 million years to make one complete orbit around the Milky Way. 230 million years.
When the dinosaurs were around, they were on the other side of the park.
Right, right.
Yeah,
they had a different set of stars to look at night. They navigated by who knows what constellations the dinosaurs cooked up.
When I share the recording of tonight, the chat file will be something you can download, so you can have all the links that are in there. That'll be available for you to download, and you can check out all these links, including my talk.
Great class, thank you.
You're welcome.
Thank you, Peter.
We'll see you next week.
Thank you, Peter.
Thank you.
Yeah.
Yeah.
Yes.
Okay, clap hands. Thank you, Peter.
Hi, Casey. All right. Well, thank you for joining us, and we'll see you next time.